All right, guys, so welcome back to part two. We're going to take a look. I mentioned section 5.3 pairs really well with what we've been doing in terms of the content and like the level of our concepts. So section 5.3 is about counting methods and then more probability building on what we're doing. So we're going to kind of take a minute and think about how being able to count our options helps us. Being able to visualize and count our options is essential to being able to calculate a probability. If you can't decide how many things are success, then you can't really calculate that ratio and get your percentage. So let's take a look. In terms of trying to understand vocabulary, we're going to run into independent and dependent events. And these are kind of what we would expect them to be. We would say that two events are independent if one doesn't affect the other. Now, in this case, we want to start expanding how we're thinking about our probability. In part one, we thought about one roll of the dice, one card, one person, like one family, and whether they own a dog or not. We're going to start thinking in terms of sequencing. So instead of one pick, we're going to think about, well, what if I pick 10 cards? Well, now that's 10 events in a row. A sequence of events has the opportunity to be independent or dependent, or the events in the sequence could be independent or dependent. So think about the deck of cards. Let's say every time I draw a card, before I draw another one, I put it back. So think about that, resetting the deck. I draw that card, I put it back. 52 again, I draw it, I put it back. I always have the same 52 cards every pick. Versus if you think about drawing a card and now putting it aside. Draw the next one, put it aside. Now your pool is shrinking. In other words, what you did affects what you have next. So it's kind of an example of what we're talking about. The replacement gives us independent picks, and the setting aside and not replacing gives us things that are dependent on what just happened. Let's take a look at variations of the scenario. So we actually just did this one together. Draw a card and put it back. Okay, that's independent. I draw two cards. This is a little different than the 10 we just did, and neither of them is placed back. So whether you're drawing one card and putting aside, or another card and doing it separately, or you do two together, it's kind of the same idea. This is dependent. When you draw the first card and put it aside, the chance of the second is affected. So sometimes we'll have to think about, are these independent events? If they are, life becomes easier. If they're not, we have to modify, very similar with what we did in the addition and subtraction. So in this case, we've talked about the pair of dice. You toss a pair of dice. Now, this one needs maybe a little more explanation. We're thinking about the number on the first and the number on the second. In this case, the number that you get on the first doesn't affect the second. In other words, the first die isn't tied to the second die. So let's talk about the counting principle. In other words, how this independent and dependent affects how we count our situations. We saw it a little bit already with the dice, because when we had 6 options for our first die and then 6 more for our second, it ended up giving us 36 total options. We saw this multiplication happen, which is exactly what we're going to see as the foundation of our counting principle. The counting principle says if you have 2 independent events and there's m ways to do the first, n ways to do the second, then there's going to be m times n ways of doing both. It's almost like, one of the ways I like to think about it is, let's say you have 2 shirts and 3 pairs of pants. You don't have 5 outfits. You could pair the first shirt with the first pair of pants, the first shirt with the second, the first shirt with the third, and then the second shirt with the first pair of pants, the second or the third. You have 6. You have 2 times 3. So think multiplication whenever you are trying to count up sequences. Okay, whereas when it's one event, before we had addition and subtraction. So we have to be careful because it can be easy to confuse our scenarios. We'll look for some keywords as we go through some examples. So you roll 2 dice, or a pair of dice. How many different ways can the dice land? Did that one. 6 times 6 gives us 36. You flip a coin and then you roll a single die. How many outcomes? So think about the coin first. A regular coin has 2 sides, heads and tails, that we can differentiate. And then, so it's 2 options. And then rolling a single die, we have 6 more. So in total, this is going to give us 12 outcomes. Okay, so let's see, cut this off just a little bit. I'm going to try to move my pictures so I can see this better. There we go. That down. So you have 3 options to vote for president, 2 options for senator, 2 for representative, 5 for the judge. How many different possible ballots? Now, when they say possible ballots, I think they're using the term a little bit differently. In other words, how many different ways could you vote? Now, in this situation, we kind of want to remove the other constraints. A lot of times when you get your ballot, if you're voting Democrat or Republican, you don't get all the candidates. But think about this in a much more simplistic way. What if we just had 5 choices? Let's see, 5 choices for the judge, 2 for the representatives, 2 for senators, and 3 for president. And you can vote for anybody in each of those categories. So what we're going to do for all the different ways we could create and turn in a ballot, think about it like that. Like how many different options for people that you're voting for can you have? So the key is here, instead of just 2 things happening, we have a longer sequence. It's still multiplication. We're going to have 3 for the president, 2 for the senator, 2 for the representative, and 5 for the judge. Multiply them all together. So I think that, sorry guys. Each selection is independent. We don't vote a straight ticket. We're just multiplying them together. All right, so let me pause there for just a second. Does anyone have any questions? Either you can unmute yourself and ask or type into the chat box. Okay, so let's go ahead and go on this one. For our next one, we're going to think about how many license plates we have. So guys, I'm trying to get these pictures to a good place there. I don't know if the recording will pick that up or on your view it picks it up. Your pictures kind of cover part of my slide here. So when we look at this license plate, your license plates typically are a combination of letters and numbers. And we're going to assume that in North Carolina, at least, we have 3 letters and 4 digits. So 3 letters, a dash, and 4 digits. How many possible combinations, possible license plates of this form are there? Now, if there are any other like specialties where you have all letters or all numbers, doesn't account for that. But just of this form, what we want to think about is placeholders. We have 3 and then 4. Okay? 3 placeholders and 4 placeholders. But what we have to do differently in this one is think about what goes in each placeholder. In the first placeholder, think about the first placeholder can accept a letter. And we don't have any restrictions on what letter. So there's going to be 26 things I could put in that first spot. 26 things in the second, 26 things in the third. When I get to my 4th spot, 4, 5, 6, and 7 are all numbers. And here we have single digits. You could put a 0, a 1, a 2, a 3, 4, all the way through 9. Now, be careful here. 1 through 9 would be 9 digits. 0 makes 10. Okay, so you have to be a little careful and ask yourself, like, what are my choices? If they tell you only 1 through 9, that's going to be different than 0 through 9. Now, keep in mind, if you said 10, 10 is really a 1 and a 0 combination. So we really only have 10 digits we can look at. So let's take a look at what that looks like. It always helps me to kind of write out a blank diagram and then fill in what's happening in each space. Now, in terms of condensing this, you could write this as 26 to the 3rd times 10 to the 4th, just using exponents. Or if we actually calculate that out, over 175,000 different combinations. So what we're going to see is with multiplication and repeated events, things are going to get large quickly. So this last question, just kind of a thought question. Will North Carolina exhaust all possible plates in the next 10 years? Well, what are they even asking on that, right? They're asking like, what if you gave out all of those license plates? That means that we would only have, well, we could round up to 176,000 to give. And then we have to ask ourselves, well, do you have more drivers in that? Now, how many drivers we have in North Carolina? Well, that depends on our population, right? Our population in North Carolina, I believe, is several million. We're not 1,000 people or 10,000 people, right? That's more the size of a small city. We're millions. So if you have millions of people, not all of them are drivers, but you have to think, is that going to be enough? In this case, that doesn't quite seem enough for all drivers if we're getting a new plate. But think about what could happen. What if we made different combinations, right? This was solely based on 3 letters and 4 numbers, right? What if we had the option to have 4 letters and 3 numbers, or to have no dash and to have something different? So in this case, they probably would consider that, right? Maybe vary those based on type as an additional piece of classification. So let's take a look at this next one. So suppose you win the lottery and want to keep it a secret, but in your excitement, you tell 2 of your closest friends, bad idea, who then also are so excited that they tell 5 of their friends. I want you to think about that, like each one of those 2 closest friends tells 5 of their closest friends, right? So think about we're creating a tree here. Now, each of those 5 friends tells 3 of their friends. How many people now know about your winnings? So when I think about this, I think about a tree kind of branching off 2, and then each of those 2 branches off into 5, and each of those 5 branches off into 3. The way I've organized this one is, instead of making our tree diagram kind of go that way, the branches look a little different. So there's our first person. That's you, right? You're the person who won the lottery, and you just told 2 of your closest friends. So there's our 2. Then each of them tell 5 of their friends. So 5 and 5. And then each of those 5 tell 3, right? So 3 that they tell. So hopefully that organization with the colors helps a little bit, but think about how many dots we have now. You can think about the first one as 1 times doesn't change our answer. So 1 times 2 times 4, or excuse me, 1 times 2 times 5 times 3. Now, if you do 1 times 2 times 5 times 3, that should equal the same thing as counting up all of this. Okay? So when we think about this, 42 people who know. Now, this is a little bit tricky because the 42 is counting all of these. Let's count and make sure, right? So if we're not sure if this works, we have a visualization. Will it actually give us 42? So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43. Now, why did I bother to count all of that? Well, partially because this initial person, if you just remove them, the 1 times doesn't add anything. But when we're writing it like this, that 1 is part of the picture. So part of the reason when you multiply the 5 times 3 times 2, or 2 times 5 times 3, you get 42. But this picture has 43. This multiplication doesn't count you. And I think this question, if I were putting it on a test, and I'll try to scan your WebAssign for this too, it would be better to say, how many other people, like besides you, now know about your winnings? This gives you the other people. It didn't count the you part. Okay, so don't stress too much about that. The important part is you've got a multiplication effect. It's not just 2 plus 5 plus 3. Adding severely underestimates this situation. It has to be multiplication. So any questions here? Pause for just a second. All right, so let's take a look at winning a prize. So in this case, it asks us, in how many ways can we select 3 people from a group of 11 and award them first, second, and third place? First, second, and third prize. So I want you to think for a minute. In a normal prize scenario, there's some sort of criteria for winning, like you ran the fastest or you got the most number of points, something like that. But in this case, we're going to think about Like we're just randomly awarding first, second, and third. That kind of helps our situation a little bit, because in a group of 11 people in real world scenario, not everybody has an equally likely chance of making the highest grade. For example, if it's like a math competition, you might have people who are higher probabilities based on their background, how many math classes they've had, how much they like math, all that kind of stuff. So what we're going to think about is any of those 11 people have an equally likely chance of having the first prize. Pick the name of the hat, give them the first place, your first prize. So think about this as, when I pick my first prize, I have 11 people to pick from. But then I don't want to give the same person second prize. So I have to set them aside. They already got their prize, and I've got 10 people left to pick from. Give them their prize, set them aside. Third place, I have 9 people to pick from. This is actually showing you that it's not the same number again and again. You have 3 spots, but you don't replace. So it's kind of like the cards in that situation. 3 spots, and then 11 for the first, 10, and finally 9. So in this case, we multiplied those 3 numbers, being careful to account for the people we take out instead of just 11 times 11 times 11. So just be careful that you're reading and thinking about, if it doesn't say replacement, you think about the context and whether you would naturally replace or not. All right, so let's take a look at putting this into a formula. Now, we've done all this multiplication, and it turns out that this gives us a formula, right? The counting principle helps us with probabilities. What we're going to do is now translate counting up the totals to probabilities. So here's what we'll say. If 2 events are independent, then the probability of event A happening and B happening, the key word is and with multiplication. Remember back to part 1, it was or for addition and subtraction. But if you're doing an and, the probability of A and B is the multiplication of the 2. So the idea of multiplying is because you're doing repeated events. When you're doing this happening and that happening, we're going to think about 2 selections or 5 selections or 10 selections. Let's do an example. What is the probability that you draw an ace followed by a jack if you put the first card back into the deck and shuffle? So a couple things on this. It's with replacement. We're putting that deck back. We're resetting the deck. In this case, we're looking at independent events, and it's telling us we can just multiply. So if we think about an ace, there's 4 aces in our deck, 52 options. If we look at that deck of cards, 4 jacks, 52 options. And I'm able to think about the 52 because I'm resetting the deck. I start with 52 both times. Okay, so 4 out of 52 times 4 out of 52. So notice this number might be a lot smaller than you think. If you just do 4 out of 52, see, I didn't calculate that number. Let me pop Desmos up here. Sorry, my technology is being a little trickier. So if we just type 4 over 52 into Desmos, let's get that as a decimal. We're getting about 8%, 0.0769, so about 8%. But then when we're looking at this case, then when we multiply these, we're getting something that's close to not even 1%. So what's happening is when you multiply 2 decimals together, you get smaller numbers. 0.08 times 0.08, that is itself rounded. The 0.08 was rounded, so we're getting a lot of error. Gives you 0.0064. Like the decimals with multiplication make things get small quickly. Kind of like on the flip side, when you multiply numbers bigger than 1, multiplication makes you expand quickly. So think about this. Don't get confused. This is a very small chance. 0.59% is not even 1%. It rounds to 1%. So let's see. I think you guys, make sure you guys can still see this. I think it took me out of view here. Okay, let's try this. Type into the chat box. Can you guys still see my slide? Yes, okay. Somehow I can't see my slide. Let me see where I minimize it. If not, I'll restart it. Okay, let's see what I did. Oh, here we go. Okay, so I think that it's working for us. You know what, guys, I'm going to just stop the share. I'm a little bit worried that it's not, that you guys are seeing a different thing than me. So I'm going to, sorry, bear with me here. I'm going to get that PowerPoint back up. And just reshare it. I want to make sure when I upload the video, and you guys aren't watching live, that it catches everything here. So, okay. So we did this one with our prizes, sorry. And then we just did this one. So let's take a look at another variation of this. So another variation is if we think about defining probabilities as with geometry. So instead of a box, I want you guys to think about a dartboard for a second. If you think about a dartboard, you have different sections color-coded different ways. So you might have the center a different color as you go out, and then you might have strips this way. So you're dividing something that's a geometric area into different sections. Now, those dartboard sections are actually kind of tricky to calculate in terms of areas. They're like little pie chunks, but sometimes the pie chunks have the middle missing. So it's like a piece of pie with the first bite taken out. They're not quite as easy as they might sound. So in this case, we're going to simplify it by looking at a box with 3 colors. A third of the box is red, a sixth is blue, and a half is white. 2 tiny pebbles are tossed in the box without aiming, and the colors are recorded or noted. So in this case, are they tosses independent? Yes. Sorry, made that go a little fast. Here, whatever I do on the first doesn't affect my second one. Then if we think about the probability that both land on blue, so the chance that my first lands on blue is 1 out of 6, because think about a sixth of the box is blue. So your probability corresponds to your area, the proportional amount that you have taken up by blue. And then if we think about both, that means the first has to land on blue and the second. First and second is another way of saying both. Learn to start recognizing an and or an or. It's not the first is on blue or the second is on blue. Both on blue means first is on blue and the second is on blue. So in this case, we have to do blue and blue. Since we have independent tosses, we multiply, and the chance they're both on blue is a little under 3%. Now let's take a look at our next one. The probability that first lands on blue and the second is on red. So first on blue and second on red. It's going to be 1/6 times 1/3. So we multiply these together and we get about 5.56% when we round that. And let's take a look on this one. Does it matter if it is blue followed by red or red followed by blue? This is kind of a weird way to ask this question, but what it's asking is, in this case, first on blue and second on red is very specific. That's going to be different than blue and red, like the way we wanted, and then red followed by blue. Right? That's different. So think about, for example, if your name is on the stone, the pebble, and you're tossed into the blue group first, and then your neighbor is tossed into the red group. Is that different than them being tossed into the red and you like being swapped, right? Yes. If you think about your names being attached, swapping you to a different group. So, see what they wrote here. Apparently, maybe I'm misinterpreting this question. I thought I had was thinking about what they were asking. Sorry guys, let me read this again. Does it matter if it is blue followed by red or red followed by blue? Oh, okay, I see the way they're asking it. Yes, it matters in terms of counting it up, but you still had 1 pebble in one and 1 in the other. So if you had your names attached to it, who is on each name matters, but what they're asking is, they should have phrased this a little differently. The question really should have said, is the probability of blue followed by red the same as red followed by blue? They're not the same, right? They're different if you put names on it. And if you guys are hearing screaming, I apologize. That's my kiddos upstairs. I'm not sure how much that'll come through or is coming through. But if you want to calculate the probability of blue than red is the same as red than blue. In this case, it would be 1 times 1/6 times 1/3, and then on the other 1/3 times 1/6. So again, kind of bad wording on this question. Does it matter? Well, if it's people assigning it to groups, yes, but the probabilities are going to be the same, which is what they were kind of getting at here. So let's take a look at the at least. At least probabilities are our last kind that we're going to take a look at today. And we'll probably end up doing a few more of them next time, specifically because they're the trickiest. Now, what I want you to think about with probabilities is a probability of at least is really a complement, but a complement in disguise. So think about if I said, I'm going to give you a box of cupcakes, and they're either chocolate or vanilla. And in this case, if we want to know the probability of not getting a chocolate, I kind of need to know your probability colors. Like, do you have 5 and 5? Like, that's going to matter. So in this case, like a box of 10 and 5 and 5 is different than a box of 10 with 4 and 6, right? So let's think of a simpler example. Let's think about coin flips. Coin flips, when we talk about a coin flip, we could flip a coin 10 times in a row. Okay? Like 10 different selections, 10 different cupcakes. Right? But the cupcake example is harder, right? Maybe we'll return to that if we have time, but nail down some numbers. But let's think about the coins. Let's say you rolled or you flipped a coin 3 times. So think about that tree diagram. Heads or tails in the first, heads or tails on each of those, 4, and then heads or tails on each of those. So if we think about that, what we really have is 8 possibilities. And the probability of not getting heads, think about not getting heads. Well, if you had heads and then heads and tails, heads and tails, heads and tails, the only way you can not, or you can get, sorry, at least 1 tails is the same thing as not getting heads. Or excuse me, I said that wrong. Doing a terrible job. I'm hearing my kiddos upstairs screaming. They are distracting just a little bit. So let me start that over. That was not good. So if you said the probability of flipping your coin 3 times, and the probability of at least 1 tails. Let me actually switch this over and write this down so that I can make sure I say this right. Sorry guys, let me stop the share. I'm going to switch us over to the paper. Okay. So if we are looking at 3 flips, I have to write things down, you guys. I'm not good at the talking. I do a lot of gesturing. But if you think about 3 flips, heads and tails. Okay, that's a big tree diagram, right? I wrote it out to illustrate this is a lot, right? This is going to be much longer if I had 10 flips. No one wants to draw 10 of those. But if I now attach a question, the probability of, let's do at least 1 tails. Forget if I said something different before. Let's look at this one. So at least 1 tails. Well, think about how success can happen. I'm going to highlight success in green. At least 1 tails, well, 3 tails would definitely be success. 2 tails would work. That one would work. Like that end would work. This path would work. This path would work. That path. Tails, think about what we didn't circle. What we didn't circle was the all heads. So think about complements. When you're doing at least 1, it turns out at least 1 is always the complement of none. So another way to say it is, if you could tell me how many ways none happen, then I'll subtract that away. So anytime you hear at least 1, 1 minus the probability of none. Now, get back to numbers on this one. For at least 1 tails, there were 7 options if we count these up. 7 options out of 8 possibilities. And then think about if we did 1 minus 1/8. Well, this is really 8/8. So that comes out to be 7/8. So it's that idea of doing the direct way, counting them all up, or doing a complement. So here's what I want you to remember. The probability of at least 1 is 1 minus the probability of none. So I'm going to stop. Sorry, guys. Touching the iPad there. I'm going to stop the share. And then, another one paused. I'm going to go ahead and share our PowerPoint again. Okay, so let's put this into a context. So suppose the probability of catching the flu from someone is 3.2%, low probability. But what is the probability that out of 10 people, at least one of them has the flu? This is some awkward wording too. I think the way they're saying it could be better, but let's not pick too much over those. We'll finish this one and then that'll wrap it up for today. We'll pick up some more at least next time. So what they're saying is the probability of flu is 3.2%. Convert that to a decimal, 0.032, making sure we're careful with moving that decimal place. So then what is the probability that out of 10 people, at least one of them have the flu? Again, bad way to word it, but it's kind of saying the probability of someone having the flu is 3.2%. I like that better. The probability of someone having the flu is 3.22%. Like catching the flu or getting the flu, being contaminated, right? Now, you're either sick or not, but they're saying if you looked at everybody, 3.2% of the population has the flu. So the probability that out of 10, at least one have the flu. So think about it as success or failure. We don't want to draw success, failure, flu, no flu 10 times, like our tree diagram out that many times. 3 was bad enough on our last heads and tails. So when we think about at least one of them having the flu, think about this is a shortcut. It's a little tricky. I'm going to go over more of these next time. But you do 1 minus the probability that nobody has the flu for each person. So this 3.2% has a complement of 0.968. That's the probability that a single person doesn't have the flu. So then 10 people who don't have the flu gives us 0.968 to the 10th. Then if you do 1 minus that, then now you're getting about 27%. So what's happening is you're having to do a complement for not having the flu, 10 of those, and then at least one having the flu is the complement of no one having it. It's like you're doing 2 complements and exponents thrown in. This gets a little bit tricky. So the at least probabilities are what our next lab is going to focus on. So what I'm going to have you do, I'm just going to kind of preview this next part. I know we're almost out of time, guys, and you have other things to do. There's going to be some more at least. So what I'd like for you to do is read through these at least probabilities and then try them. We'll go over a few of them next time and talk about how this is going to look in your next lab. So what else do I want you to do? I'm going to be updating your WebAssign. Right now, your WebAssign is sectioned, one set for each section in the book. I'm actually going to combine these 2 sections together into one and release it. I'll have that up in just a little bit. I have to actually make that change. So let's see, it is 1:25. By 2 o'clock, I'm going to have your WebAssign for this section edited down. If you already started on this, don't worry. I can go in there and see your work. But after 2 o'clock, you're going to have that WebAssign open. Try to do as much of that one combined section with 5.1 and 5.3 together as you can. That'll make Wednesday go smoother when I talk about more at least, and then also work on your lab. Keep in mind, Wednesday, we're not live streaming. What I'm going to do is look through these, any WebAssign questions that come in. So let me know if you're struggling with any of those. And I will record a video ahead of time. Part of the reason for this one is I have a meeting that's already scheduled for Wednesday. So what I'll try to do is kind of make it a mix of live streaming and then pre-recording. Try to be with you guys live as much as I can when other things don't pop up. But this is a meeting that is kind of not movable. So again, that will be our plan. I will send you guys an email reminder so that everybody sees this in the class, just of everything to keep in mind once everything is up and loaded. So I'm going to stop sharing my screen and open it up to questions. If you have questions, you're welcome to keep on and ask. If you don't, you're welcome to go ahead and leave. I'll give it a minute and then I'll end the meeting. I'm going to go ahead and see people logging off here. So it looks like there's no questions. I'll go ahead and end the meeting and then send you guys a follow-up email later this afternoon. Thank you guys for participating and have a good rest of your day.